Hello and welcome back to part 2 of 5th chapter Radar Systems. Myself Sanjit Kumar Singh, lecturer in Electronics and Telecommunication Department at Praveen Patil College of Diploma Engineering and Technology. So in this presentation, after going through this presentation, the learner will be able to describe with a relevant sketch and block diagram the working and operation of the MTI radar, moving target indication type radar, and explain the concept of the blind speed and application, and also the automatic target detection. And secondly, the display methods, the different display methods used with the radar system will be able to describe the with a relevant sketch and the working principle of such a display system. And in the previous presentation we have seen the Doppler effect and the continuous wave Doppler radar, frequency modulated continuous wave radar. So, and in this presentation we are seeing that these two, MTI and the display methods. So here is the block diagram of moving target indication radar, MTI radar, where we can see there are two mixtures, mixture 1 and mixture 2. Mixture 2 is used for generating the signal to be transmitted. The two signals that are mixed or brought to the mixture 2 are from the two local oscillators. One is the stable local oscillator that is generating frequency of FO, and there is another higher frequency generation, radio frequency generating coherent radio frequency generator local oscillator, that is FC, is generated and is fed to the mixture 2 as well as phase sensitive detector. So mixture 2 is generating the some signal and is, after amplification through the klystron amplifier and the modulation demodulation, it is given or pass on to the transmitting antenna through the duplexer, which is acting as a switch, and the received echo pulses from the moving target or stationary target or remote object is coming back through the duplexer after being received from the receiving antenna and is directed towards the mixture 1, where it will have the transmitted frequency plus the Doppler shifted frequency or Doppler frequency. And another input that is coming to the mixture 1 is the stable local oscillator F0, and these two inputs to the mixture 1 is resulting into an output which is only the radio frequency FC being coming out, and is amplified using the IF amplifier as the frequency of FC signal is in the range of intermediate frequency, and this amplified signal is then fed to the phase sensitive detector, which is receiving another input from the coherent oscillator as the coherent oscillator, because it is in phase or it is phase locked with the say the incoming signal from the IF amplifier, and IF amplifier is working at the same frequency. And the phase sensitive detector is similar to phase discriminator, which is detecting the phase difference between the received echo pulse and the reference radio frequency that is generated by the coherent local oscillator. And output from the phase sensitive detector is given to subtractor after amplification by amplifier 2, which is comparatively a lower gain than the amplifier 1. Amplifier 1 needs to amplify it to higher, or it has a higher gain than amplifier 2, because it has undergone a delay and attenuation that is of 40 dB attenuation that may be introduced by the delay line. The delay line is making use of fused quartz, or it could have many-sided prism, where the total length the signal has traveled will be such that it will be providing the required delay time that is given by 1 upon PRF, or it is dependent upon the PRF frequency. So if the PRF pulse repetition frequency is 1000 Hertz, then the delay required will be 1 millisecond. And similarly, if the pulse repetition frequency is 1500 hertz, then the delay required will be nearly 666 microsecond. So after the amplification of this video signal will be comparable at the output of the two amplifiers, and then it is fed to the subtractor. The subtractor is actually subtracting the complete scan from the previous one and displaying only the difference. So in this MTI, it is actually making both the technique of pulse and the Doppler technique to improve the performance and measurement capabilities. And in this system, it is evaluating the successive echoes to determine the phase shifts that indicate when a target is moving. So the output of the subtractor will be a MTI video that can be indicated on a display system. So Doppler frequency shift causes the variation in the phase difference. A change of half cycle in Doppler shift would cause an output of opposite polarity in the phase detector output. The output of phase detector will have an output difference in magnitude and polarity from successive pulses in case of moving targets, and for fixed target, magnitude and polarity of the output will remain the same as shown in the figure. So here we see the due to stationary targets, the echoes are cancelled out from the present scan. The previous scan is subtracted and hence echoes are cancelled out, whereas that of the moving target, a moving object, there are some loops formed that indicates the presence of a moving target. So the concept of the blind speed is that the blind speed is actually a radial speed of the airplane or the object at which the phase shift of the echo signal has the value plus minus n times 360 degree or 2 pi radian between the two pulse periods. So blind speed can be given as Vb equal to lambda by 2 PRT, or where lambda is the wavelength of the transmitted signal and PRT is the pulse repetition time. So that can be also written as, if the target is moving a half wavelength between successive pulses, the change in the phase shift will be precisely 2 pi radian, and we may state that the blind speed Vv will be equal to PRF into n pi by n lambda by 2, PRF n lambda by 2, where Vb again it is blind speed and lambda wavelength of the transmitted signal and n any integer. So we can calculate the first and second and third and fourth blind speeds using this formula. So this occurs, the blind speed occurs because of the relationship between the transmitted pulse repetition time PRT and the received pulse repetition rate. The Doppler pulse repetition rate is different between the transmitted and received pulse repetition rate. So a solution to this blind speed problem of blind speed is to vary the PRF. If the pulse repetition time is varied or the pulse repetition frequency is varied, then we can detect the moving target easily. The blind range for a radar system is the distance occupied by the transmit pulse and setup time for the receiver. Non-Doppler radar are blind for the duration of the transmit pulse. So the non-Doppler radars are blinded when it is in the transmitting mode due to the high power. Now here is the display methods. There are different display methods as given in the diagram sidewise. it has the A scope, PPI, sectored PPI, B scope, E scope, and C scope. So these are the different display methods, out of which A scope and PPI are the more commonly used. A scope is the it presents only the range of the target and the relative strength of the echo. Normally used in weapons control radar system, A scope normally uses an electrostatic deflection (CRT). The sweep is produced by applying a sawtooth voltage to the horizontal deflection plates. The electrical length or time duration of the sawtooth voltage determines the total amount of range displayed on the CRT face. So A scope displays is simplest and is used in older radar sets only as a monitoring oscilloscope. It is simply displaying the range versus amplitude of received echo signals, as we can see in the adjacent figure. So in this first blip is heard, that is due to the transmitted pulse as a reference, and the other blips are due to the ground clutter, or it would be the grass noise and the actual targets. The second type is the plant position indicator, or PPI. So PPI scope is by far the most used radar display. It is actually an intensity modulation type display, where both the range and azimuth angle of the target, the direction of the target, in a polar coordinate display of the area surrounding the radar is shown. So its own position is indicated by the origin of the sweep or center, which is normally located at the center of the scope, but may be offset also. So PPI uses radial sweep pivoting about the center of the presentation. The sweep rotates on the display just as fast as the radar antenna, say typical 6 rpm. This results in a map-like picture of the area covered by the radar beam. A long persistence phosphorus screen is used so that the targets remain visible until the sweep passes again. So due to long persistence, it is the target is seen till next sweep arrives. So PPI screen diameter could be of 30 or 40 centimeter diameter, and this PPI is plant position type indicator is suitable with the search radars and for conical scanning. So in the adjacent diagram we are seeing the display PPI methods, where a dot bright spot is representing the moving target, whereas due to the stationary targets it is cancelling out all the echo pulses. Now the automatic target detection. So the performance of display methods in radar system operators may be erratic or inaccurate when people staring at the screens for long hours do get tired. So therefore the output of the radar receiver may be used in a number of ways that do not involve human operators or human. One such system may involve computer processing and simplification of the received data prior to display on the radar screen. Other systems use analog computers for the reception and interpretation of the received data, together with automatic tracking and gun laying or missile pointing, that is electronic countermeasure. Or now this topic has been included here. Compare continuous wave and pulse radar as given in the unit outcomes, fourth unit outcome of this chapter. So continuous wave radar and pulse radar can be compared on a number of parameters. These parameters, as we can see, For the continuous wave radar, the system uses modulated or unmodulated continuous signal for transmission, whereas the pulse radar system, it will be using the pulse modulated signal for transmission. And in continuous wave radar, circulators are used to separate or separate antennas are used for providing separation or isolation between the transmission and reception, whereas in pulse radar, duplexer is used. In simple continuous wave radar cannot indicate the range, that is a drawback, whereas pulse radar can indicate the range. The Doppler frequency shift of echo signal is useful for indication device in continuous wave radar, whereas pulse radar, the echo power received is useful for the indicating device. Continuous wave radar is making use of lower transmitting power, whereas it requires completely higher transmitting power in pulse radar. The circuits are simple in continuous wave radar, whereas pulse radar system somewhat complicated circuit will be used. The performance is unaffected by stationary targets in continuous wave radar, whereas in pulse radar it is sometimes affected. And continuous wave radar, because the receiver is on all time, it can operate down to zero range. So zero range is one of the advantage of continuous wave radar, whereas that of the pulse radar, it cannot operate down to zero range. The system gets confused by presence of large number of targets in continuous wave radar, whereas it is not affected by not affected in pulse radar system. One of the application is of continuous wave radar is in aircraft navigation for speed measurement, whereas pulse radar application is in mapping of airport area. So MTI radar used in mapping or navigation application. So thank you very much for patiently listening